What we're looking at here is a Rosemount Model 1151 Smart Gauge Pressure Transmitter. It looks remarkably similar to a differential pressure transmitter of the 1151 series. However, there is one noticeable difference. If we take a look at the capsule assembly, the actual housing that contains the sensor measuring the pressure, we see a high side and a low side. But if we look carefully at the low side, we'll notice there's no port, as there is on the high side, to apply a pressure. Neither will you find a port on the other side here. You have a vent attached to the high side, a bleed vent, but again, there's no opening whatsoever to on the low side to attach a process pressure, which means that this transmitter cannot be used to measure differences of pressure in the same manner that a true DP transmitter can, where it has a high port and a low port. The low side here is simply vented to atmosphere, so it functions to measure gauge pressure and gauge pressure only. However, the electronics of this transmitter is pretty much the same as what you would expect to find on any sort of differential instrument made by Rosemount. If we take a look at the cover here, we remove this cover on this side. This covers up the connection terminals for the 4 to 20 milliamp circuit. This is what we refer to as a loop-powered transmitter, which means it does not have its own power supply. It does not even have separate power supply terminals. It uses the exact same terminals right here to convey the 40 to 20 milliamp information, as well as to receive power from an external source. This is a loop-powered transmitter. It depends on a power supply connected in series somewhere in that series loop circuit to power this device up. And then once that power supply is connected, this transmitter regulates the amount of current in that series circuit by acting as a dependent current source. Therefore, if we apply a greater pressure to the high side of the diaphragm, that causes the diaphragm to flex. The electronics inside here will measure that motion and convert that into a rising milliamp signal. So the more pressure we apply, the greater current we get out of this, ultimately towards 20 milliamps if we apply the upper range value of pressure. So this is acting to throttle the amount of current through the circuit, to limit the amount of current through the circuit according to how much pressure is being applied to it. And we'll notice, in addition to the signal terminals, here we have the plus signal terminal and the minus signal terminal, we also have a pair of terminals labeled test, also plus and minus. The test terminals are designed to provide a very easy way of tapping into that 4 to 20 milliamp current signal without actually breaking the circuit open at any time. Underneath this housing, in parallel with these two test terminals, is a diode that is normally conducting the 4 to 20 milliamp signal. If we were to connect an ammeter across these two terminals, the very low resistance of the ammeter would short past that diode, effectively turning it off and allowing the entire 4 to 20 milliamp signal to pass through the ammeter. But if the ammeter ever breaks open or is disconnected, the diode once again turns on and allows all the current to go through it. That's a very clever way of intercepting a 4 to 20 milliamp DC signal without ever breaking the circuit open. Because if you break the circuit open, that means whatever instruments are connected to this transmitter would then lose that signal. The transmitter would power down, and those other instruments would see a dead signal. This way, I can tap in with an ammeter for test purposes, for diagnostics, or on a semi-permanent basis by having a remotely mounted milliamp meter serving as a local indication to operators connected in parallel. And if that local indication ever fails in the open state, that diode takes over and maintains continuity of the circuit. I can reattach this cover and remove the cover on the other side of the transmitter, which houses the smart electronics. Of course, this is easier to do with two hands. Here we go. Spinning it around and take the other cover off. Underneath this cover is the smart electronics package, housing the microprocessor and all the electronics necessary to interpret the motion of that diaphragm. We see a span button and a 0 button. Pressing these buttons and following a particular procedure will set the lower value and upper range values of the transmitter, respectively. We also see a couple of small switches, one for failure mode and one for security. This being a smart instrument, it characterizes the differential capacitance sensor and is able to correct for certain nonlinearities given with pressure and temperature, and in doing so provides a more accurate pressure indication than we would have otherwise with analog electronics. Furthermore, being a smart instrument, it has the ability to communicate digitally over the same two wires that we saw underneath this cover same two wires here that conduct the 4 to 20 milliamp signal can also carry a frequency shift keyed digital signal, which Rosemount refers to as HART, H-A-R-T, and that HART signal is able to communicate information digitally between the transmitter and a host system. That host system can be a handheld communicator, or it can be a HART-enabled control system such as the Emerson Delta V. So the smart capabilities of the transmitter make it very versatile in use. It's very easy to rearrange the transmitter using data sent over the HART protocol. It is also very easy to access diagnostic information. We can tell if certain failure modes have occurred inside the electronics through the HART communications.